Thank you. Sorry. Yeah, I wrote the title too small the first time. Sorry. Yeah, so I'd like to thank the organizers for having us here and having me to speak. Yeah, so I think, as I said in my abstract, this is a somewhat speculative talk in the sense that I haven't exactly finished doing the research, but I also hadn't exactly finished doing the research 3 years ago when this conference was meant to happen. So I figured that I might as well talk about it now anyway. Yeah, so just to give some sort of motivation, I mean, I'm going to be sort of talking mainly about definitions and sort of abstract nonsense. And so I should say something about why I actually care about this stuff, which I do. So one piece of motivation is that, so we have this theory of Cubespaces and null spaces, and it has these great applications and it's very useful. But it feels sort of a little cut off from the rest of mathematics in some ways. So yeah, so it has applications in dynamics and additive number theory, but it's difficult to sort of, we have to start from the ground up, right? We have our own definitions and we use them to develop our own theorems and our own theory. It would be really great if we could just sort of import content from other areas of mathematics. So let me just say, reconnect. So I think that would be an interesting goal in itself. Yeah, maybe more specifically, I can say that, so a lot of our definitions and a lot of the proofs and things seem a little ad hoc. So yeah, it'd be useful to import theory or motivate definitions. So one specific example of this that comes up is so in Cubespace theory, we have this sort of co-cycle theory, which is very important. Sort of most of the major results about nil spaces use this co-cycle theory in some way. So we have this theory of co-cycles and co-boundaries and things, but there are sort of a certain number of things that are strange about it. So firstly, it's just say it's strange. And by that, I mean, it doesn't look like doing cohomology that you would do in a sort of a topology class or an algebra class. That are co-cycles, we call them co-cycles and we call them co-boundaries, but it's not obvious that they're the same kind of thing as other kinds. And also we don't have any, yeah, so maybe I'll say in particular, there's no sort of, what does this have to do with the snake lemma, right? So we can't sort of just define our homology groups in terms of long exact sequences and short exact sequences and all that kind of usual stuff. That just doesn't seem to be the right way of doing it. And in particular, that means that we can't compute any of these things. And this, I think, is sort of one of the more embarrassing things, that we can say some things about these co-cycle groups that, they're trivial or they're not trivial, but if I give you a specific example and say, here is FP, what's its cohomology group? We don't know. We don't know if it's, yeah, we have a very limited ability to do calculations. And this, I think, kind of does hold us back. Okay, and my last piece of motivation, this is all rather vague, is that I want to be able to generalize the Cubespace theory we have in order to solve the structure theory or the inverse Gowers theory for these more general Hurst-Krauss seminorms where we don't currently have an inverse Gowers theory. And I just sort of believe that in order to do that and stop everything becoming incredibly complicated, we need to do things in a more systematic way. So I want okay. Great. So, okay, having said all those vague things, let me quickly recap the sort of existing cube space theory that I want to talk about. So all the things I'm going to say are going to live in the very elementary part of this, right? I'm sort of mainly interested in definitions and the sort of the most basic part of the theory rather than the really hard part of the structure theory. So okay, we had Pablo's talk at the beginning of the week, but that was a long time ago. So let me remind you what the basic definitions are. So actually, I'll call this definition prime because this is not quite the same definition as Pablo wrote up on Monday. So a cube space consists of, so I can define a cube space like this. For every n, I'm going to have a space of n cubes. So for every n, yeah, there's a space by which I mean a topological space. You can assume it's compact if you want to, of n cubes. And between different kinds of cubes, I have sort of maps between them. So if I have a two-dimensional cube, I can take a face, and that gives me a one-dimensional cube. So let me just say, for certain functions, gamma from 0, 1 to the n to 0, 1 to the m, a continuous map let's call it C gamma from the m cubes to the n cubes. Okay, so yeah, it really does go this way around. So just to give a quick example, if I have gamma as a function from, let's say, the 0, 1 to the 1 to 0, 1 to the 2, given by taking 0, 1 to 2 of the vertices of 0, 1 squared, let's say this vertex goes here and this vertex goes here, then the corresponding map C gamma from 2 cubes to 1 cubes would take a cube and single out its left-hand face. Okay, and yeah, in general, you have, I won't repeat the definition of exactly which functions gamma, but it's sort of the ones you think, the ones that pick out faces, or in the other direction, the ones that take a vertex and sort of duplicate it onto both faces. Okay, so I was wondering if someone's going to object that this isn't actually the same definition that it's not even equivalent to the definition that Pablo wrote down. And the reason is that I didn't, normally we think of a cube as being a set of vertices, right? Sort of, a cube is determined by which vertices it has. And I didn't actually say that here. So I never said that a cube is nothing more than the total of its vertices. So let me just say a remark that, yeah, so say cube space X is concrete if I take Cn of X and I map it to C0 of X, the vertices, well, let's just say X, probably easier, 2 to the n times, then this is injective. Okay, so this says that you can't have 2 cubes which have the same vertices but aren't the same cube. All cube spaces that we see in nature have this property. They sort of, they're very physical objects, but I think it will become useful to have this more general definition shortly that maybe you could have two cubes that have the same vertices, but got there in different ways. There's this cube and also this cube. Yes. In the concrete case, Cn of x is a subset of. Oh, in the non-concrete case, this map might not be injective. There is a map, yeah. So exactly, yes. You can always write down this map because it just says, you know, take a bunch of these C gammas that take a cube and select one of its vertices, take all of the maps that take a cube and select its vertices. So this map always exists. Maybe it would be useful if I wrote C0 of x, but it might or might not be injective. And I'm saying let's assume it's injective. Thank you. Yes, thank you. Sorry. So there's a standard but lazy piece of notation that C0 of x x refers either to the whole cube space or to the set of points C0 of x. Yeah. Maybe I should be good and write C0 of x. Okay. Cool. So yeah, so that's the definition of a cube space. If we like definitions, if we like making definitions, we can get some more for free. So for example, I can define a cube. Oops, this should say a cube space. So this is the definition of a cube space. I can get many other things by just writing a different word instead of topological space. So a cube set, for example, would consist of oops. A cube set would consist of for every n a set Cn of x. So this is basically the same definition, you just don't have any topology. And then instead of a continuous map, you just have a function. So a cube set is the same as a sort of discrete cube space that doesn't have any topology. And I can do more general things. So I could write group in here. So a cube group is where for every n you have a group of n cubes. And then the maps here are assumed to be group homomorphisms. So really, I mean, in the concrete case, that's just the same as saying that the space of cubes Cn of x is a group under pointwise multiplication. Okay. So the prototypical example of a cube group would be to say if G is a filtered group, and I set Cn of x to be the Hofstra cubes on G, then this is a cube group. So these things arise naturally in the theory. And if you're particularly bored, then you can show that this is actually the only kind of cube group there is. So any, well, if I assume it's concrete, any concrete cube group actually comes from the Hofstra construction, so they're equivalent. Okay, cool. What else should I say? Oh yeah, so I should remind briefly. So to recover the definition that Pablo gave of a nil space, I also omitted several of parts of the definition. So this just says that you have cubes and you can take faces and stuff. There was also this important property of cube completion. So say that X has completion or is fibrant if every corner can be completed to a cube. So like many things, this is best shown by a picture. And the picture is that if I have let's say, a three-dimensional corner. So this looks like the following. So it's a cube with the top vertex removed. Then this can be completed. To fill in the final vertex. We're used to this definition for concrete cube spaces. Let me just remark that it also makes sense for the non-concrete cube spaces. You just say, if I have three two-dimensional cubes that all glue together in the way you expect them to, then there exists a three-dimensional cube which maps down to them in the way you expect. So yeah, so this is vital for the theory. I guess the last part of the definition that I'm missing is, we usually assume, because otherwise things get very boring, that every pair of elements is a one cube. So let's say X is ergodic. If, well, traditionally we would say that C1 of X just is all pairs X cross X, that every pair of vertices forms an edge. I guess in the abstract world, we should say surjects onto X cross X. But again, if you don't care about that, then don't worry about that. Okay, so that's more or less my review of the definitions. And I also want to recall some of the most basic level of the structure theory of these cube spaces with these extra properties, so of nil spaces. So it says that if X is a, well, with my definitions, I have to add all these adjectives. So ergodic, concrete, vibrant, cube space, then we can get a certain amount of structure just sort of without doing too much work. So in particular, it has these things called structure groups. Which are traditionally AK of X. So these are abelian groups. If X is a compact topological nil space, then they're compact abelian groups. For example, if my cube space is actually just the Hofstra cubes on some group, then the structure groups are just what you get by taking successive quotients. Okay, but even when your cube space is not coming from the Hofstra construction, there's a way purely abstractly to define these structure groups. And seem to be going through chalk very quickly. Okay, here we go. We also have the what are called the canonical factors, I think. So these are the cube space equivalent of the Hofstra factors in the ergodic world. So if we have X, then we can find this factor called pi k of X. And they form a sort of tower. So you go all the way down pi 2 of X, pi 1 of X, and then pi 0 of X, as long as your ergodic is just a single point. And the cool thing is that the fibers here are somehow the structure groups. So we have a sort of X is representable as a sort of tower of these extensions by groups living in the fiber. And so, for example, this one is basically the Kronecker from the ergodic world, and then these are the other Hofstra factors, but you can then define this purely abstractly without any dynamics or any group structure. Okay, I think that's all the review I wanted to do of that for the second. Maybe I'll try and convince you. So I've sort of been giving you these abstract definitions and these even more abstract definitions. I'll try and give you a quick example as to why you would possibly care about this abstract or non-concrete cube spaces, where you sort of don't think of a cube as just a set of its vertices, you think more generally. So let me give you an example. So if X is, let's say it's a very nice space. Let's say a vibrant ergodic null space, ergodic cube space. I mean, you can think of it as just being a nil manifold Gmod gamma if you want it. If the construction is still interesting. Then let's define a new cube space by setting Cn of, let's call it x tilde. I'm going to define this to be, so the cubes of x tilde are the cubes of x modulo some equivalence relation, where the equivalence relation is going to be, I'll say it in words. So two cubes are considered equivalent if when you glue them together, you get a cube of one dimension higher. So this is called the face relation in the literature. So yeah, where C1 twiddle C2, precisely when this sort of joined up configuration C1, C2 is a cube of one dimension larger. So yeah, the face relation. So, you know, pictorially, if I have a cube and I have another cube and I put them next to each other and they form a three-dimensional cube, then that means that the left face twiddles the right face. Okay, so I've told you what the cubes are, and then the maps are just given by nonsense, right? So just define the map from Cn to Cm to be what you get by taking this map and then quotienting on both sides. So, and you can go away and check that this is a cube space in the sense that I defined it. But for example, C0 of x, twiddle, well, this is points modulo equivalence. If my cube space is ergodic, then the equivalence relation is everything, right? Any 2 points are equivalent because when you glue them together, they form an edge. And so this is just the 1 point space. So this clearly can't be a concrete cube space unless it's trivial because it only has 1 point. So I can't have two cubes being the same if they have the same vertices because there's only one vertex. But meanwhile, if I take C1 of x twiddle, well, this consists of sort of edges modulo equivalence. And if you sort of think about it for a while, this is basically the Kronecker factor. This picks out the first structure group A1, in other words, the Kronecker. Okay, so if you don't think that this is an interesting construction, then obviously you don't care, but I'm claiming that this kind of construction is useful and it naturally puts you in this larger space of abstract cube spaces. Okay. So I think I had one more thing I wanted to recall, and then that tells me with my review. So the last thing, I just want to remind you what a tricube is. So a tricube in a cube space theory is a configuration that looks like this. So I'm going to take 4 cubes and glue them together. So take, sorry, this would be in the case n equals 2. You can do this in any dimension. So take a bunch of cubes which you can glue together in this way along their faces. And then the only interesting observation is that there's one of these logic puzzles, right? Like how many cubes are in this picture? Audience participation, how many cubes are in the picture? Sorry? 5 is one bid, so that there are 4 I can see. And then there's also one around the outside, right? You can glue all these things together and they form one big cube. I claim the right answer is 9 because I can also take this and this and glue them together and that forms another cube. So yeah, the interesting thing about tricubes is that there are actually 9 cubes in this picture. By gluing, sort of gluing pairs of them together or 4 of them together. And okay, if you've read the cube space theory, these things are sort of completely essential to proving stuff. They come up all the time. Yeah, I won't tell you how, but I just wanted to make that definition. Okay. Okay, so that was my sort of lightning review of bits of cubespace theory with some extensions. I now wanted to, so I said I would tell you about cubespace theory and homotopy theory. So I now want to give you another brief lightning course in the homotopy theory side of things. So call this simplicial sets. So the gist of this is just that there's a very similar definition, which is completely standard in homotopy theory and algebraic topology. So if I write this definition to be as close as the previous definition as possible, then it says the following. So a simplicial set. So this is not a definition due to me. This is a definition in, Hatcher or something. So this consists of the following data. So for every n, a set which will denote delta of n of n simplices. So yeah, instead of a set of cubes for every n, we have a set of simplices for every n. And again, I won't give you the gory details, but for certain maps, call them gamma, from sort of the standard n simplex, which is usually considered 0, 1 up to n. So this is a 0 simplex. This is a 1 simplex. This is a 2 simplex, and so on. So yeah, for maps from the n simplex to the m simplex, then I get a corresponding map in the other direction from gamma m to gamma n. And the way you should think about these is exactly like cubes, that this is sort of cutting out a face or something like that. So for example, if I take the map gamma from 0, 1, 2 to 0, 1, 2, 3, that takes, I don't know, maybe it just takes 0 to 0, 1 to 1, and 2 to 2. Then the corresponding map the other way around would be a map from 3 simplices in X to 2 simplices in X that just takes a 3 simplex and just picks out the space. Okay, so again, these correspond to sort of faces of simplices rather than faces of cubes. Okay, what else should I tell you? Oh yeah, so in exactly the same way as we did for cubes, this is a simplicial set. But if I want to define a simplicial space or a simplicial group, then I just replace the word set with space or group, and I replace the word map with function or group homomorphism, continuous map or group homomorphism. So I'll just say respectively, simplicial set, space or group, etc. And you can put your favorite category there, and it makes sense. Okay, so obviously the definition looks very similar. There are other similarities as well. So there's a notion of completion for simplicial sets. So we say a simplicial set X has completion, actually Kahn completion, or is Kahn fibrant, or is a Kahn complex. Any of these are valid names. If certain kinds of configurations can be completed, and those are called horns. So if any horn can be completed to a simplex, So hopefully if I draw one of my bad diagrams here, that will be a way to explain what that means. So a horn is basically a simplex with one of its faces removed. So I will try and draw that as follows. So as you can clearly see from this dotted line, this is not a filled in simplex. This is just three triangles glued together. So that's a horn. And the claim is that any one of those can be completed to a filled in simplex. And you can see by this dotted line that this is clearly filled in. Okay. So yeah, this is the analog of the corner completion property for simplicial sets. I could sort of go on, but I think it would be more convenient to write the analogies in a table. So let me do that quickly. So yeah, on the left-hand side, I'll take cube spaces. And on the right-hand side, I'll take simplicial sets. Delta n x, maybe delta n y. Less confusing. Yeah, so well, we've already seen the basic analogy that rather than the n cube n as my underlying shape, I use the simplex 0 up to n. Yeah, rather than corner completion, I have Kahn completion. What else do I have? So yeah, so remember on the left, we have these structure groups, AK of X. These sort of groups canonically associated to any fibrant cube space. If I have a Kahn complex, I can define what are called its, well, just its homotopy groups. So pi k of X, pi k of Y. So maybe I should have said sooner. So if you're an algebraic topologist, these simplicial sets are sort of fundamental to everything you do. And they really think of topological spaces and simplicial sets interchangeably. So if you're used to the idea that the homotopy groups are associated to a nice topological space, then that's exactly the same as saying they're associated to simplicial sets. They don't really distinguish between these two things. So these really are the same thing as the honest homotopy groups. You know, pi 1 is the fundamental group, pi 2 is whatever it is. These are the same objects. But you can define them on any Kahn complex in a natural way. Okay, so we have the structure groups. We also have these canonical factors. Pi 1 of X, and I'm trying to draw little pi to mean canonical factor and big pi to mean homotopy group. Okay, and these had the structure groups living as the extensions. And this actually has an analog for simplicial sets as well. This is called a Postnikov tower. And this says that you can build your simplicial set out of a sort of tower of extensions. Well, as long as it's connected, then you can put this y1 and y2 and so forth that sort of eventually give you y. And this extension is given by pi 1, and this is given by pi 2, and so on. So this elementary structure theory of Cubespaces is exactly analogous to these Postnikov towers. Maybe I'll try and squeeze in one more on the board. So here, remember I said that cube groups are sort of completely in one-to-one correspondence with filtered groups. Well, at least if they're concrete. And okay, I'll have to extend my table onto a second board. But this has again a completely analogous theorem for simplicial sets. It even actually has a name, like Postnikov towers. So this is called the Gold-Kahn correspondence. Kahn gets a lot of screen time today. And this says that a simplicial group, or a simplicial abelian group, these are in one-to-one correspondence with chain complexes. So remember, I mean, our filtered group, we have G0, which contains G1, and so on. And a chain complex, remember, is where we have some group H0, some group H1, and so on, where the now have this added condition that D squared is 0. So if you have a sequence of abelian groups like this, that gives you a simplicial abelian group and vice versa, in the same, analogously to the Hausdorff construction for filtered groups. Okay, so at the moment, I think this is a sort of exceptionally good analogy that, I mean, if you want to know more cube space theory, it seems like a very good idea to look at simplicial set theory and see what else you could carry over into this table. But I mean, it sort of begs the question really, like, is this just a really good analogy, or are these things sort of, is there an explanation for these coincidences? So yeah, it seems very lucky that when we defined our random cube spaces, we get to have these things that look like homotopy groups in the same way that in simplicial sets, you have honest homotopy groups. Yeah, this seems, we'll just say, is this a coincidence? Or maybe a better question would be, can you actually like have a map from the left diagram to the right diagram, or vice versa, right? Is there a way of taking these analogous objects and actually turning one into another? So yeah, I can nearly present an answer to that question. So so to motivate this, there's one more preliminary thing I should tell you about, which is a bisimplicial set. Again, this isn't a definition from me. This is, maybe this isn't in Hatcher, but it's on the internet anyway. So this is something homotopy theory people study. And it's sort of, so if a simplicial set has one set for every simplex, delta n, then this really has one set for every sort of pair of simplices. So a consists of a set delta nm x for every n and m at least 0. And again, I think so. Think of delta nm as being kind of like the product of the n simplex with the m simplex. So again, I think it's much easier just to draw a picture. So specifying one of these, oh, and obviously certain maps between them in the usual way. I won't write that down. So the picture that you should have is that if I make a grid with n across here and m down here, and this is going 0, 1, 2, 0, 1, 2. So a 0 cross 0 is a point. A 0 cross 1, well, that looks like a point across an edge, so that's an edge. And similarly, this is just a 2 simplex. Going down this way, a 1 cross a 0, I think of that as like a vertical edge, right? It's also an edge, but maybe it's not the same as this one. And this is again, a simplex, but a vertical simplex. But this interesting, like a 1, 1 simplex, that looks like a square. And there are again maps where you can take, you know, for example, the left face and map it to a vertical edge, or the top face and map it to a horizontal edge. And then what goes here? So this would look like a sort of, this is a prism type thing. It's a Toblerone. Right, so it's a 2 simplex cross a 1 simplex. And similarly, this is a vertical Toblerone. And this thing, it looks like a grid, where again, actually, it looks like there are 4 squares here, but there are actually 9, because this is a 3 cross 3. So, and so on. So this is what a bisimplicial set is. And so this doesn't really link up yet to cube space theory, but it almost does, right? So this is we could think of these as the two-dimensional cubes if we wanted to, right? This is a set of things that have the same kind of maps on them as cubes do. You can take left faces and right faces and up faces and down faces. We're just missing the 3 cubes and the 4 cubes and the 5 cubes. So if we, instead of having a bisimplicial set, had like a bisimplicial set and a trisimplicial set and a 4-fold simplicial set and so on, then that would sort of have cube spaces inside it in like this top left corner. And it would also have things like this, which should look suspiciously reminiscent of tricubes. So somehow in that bigger picture, things like tricubes would be part of the definition rather than just, a configuration where you take 4 cubes that happen to glue together. It would just be, first-class citizens in the definition. So let me make that definition. Just about have time. One thing before I do. So simplicial sets have these homotopy groups, pi n of x. You can think of a bisimplicial set as sort of a simplicial set of simplicial sets. So in fact, it is even a simplicial set if you formalize what that means. So what happens here is you can take like the homotopy groups of every column, which is a simplicial set, and then that gives you back a simplicial set, and you can take the homotopy groups of the remaining 1 row. So you actually have homotopy groups. This is by abstract nonsense, pi n of pi m of x. So a bisimplicial set has these sort of iterated homotopy groups where for every integer n and m, you have a pi n of pi m of x, and that's an abelian group pool. No, it's a group and it's often abelian. Okay, so the definition I want to give, and I'll stress this is my definition, this isn't in the literature. I'll call this a sigma simplicial set. And this consists, it's a very similar definition to the previous ones. So for every, well, let me see. So here originally I had every integer, now I have every pair of integers. And now I want every sequence of integers. And I'll assume they're in the right order. So yeah, I'm going to sort of assume some sort of symmetry that actually vertical edges and horizontal edges are the same thing, and therefore it makes sense only to have one kind of edge. And I'll have a set which I'll call delta A1, A2 to AK of x. And then, okay, I won't labor the point again by telling you exactly what the relevant morphisms are, but so let's say for certain functions gamma from, well, it's from the product of the AI simplexes to the product of some BI simplexes. Then there's a map in the other direction, C gamma, from delta B1 to delta A1. Okay, so yeah, so again, it's slightly annoying to write down which maps those are, but there is a complete abstract nonsense way of saying it. You take the pre-pointed monoidal category on the simplex category or something, and anyway, it's basically what you think it should be. You take faces wherever you can take faces, and so forth. And yeah, the first few instances of this, so a delta 0, a delta empty set, I guess, is just a point. A delta 1 is going to be an edge. A delta 2 is going to be a 2 simplex in the normal way. A delta 1, 1 is going to be a 2 cube, and a delta 1, 1 is going to be a 3 cube, and a delta 2, 1 is going to be one of these prisms, and a delta 2, 2 is going to be a tricube, and so on. Okay, so I'm sort of proposing this slight extension of the definition of simplicial sets. Sorry, the definition of Cubespaces, really. Okay, I'm essentially out of time, but if I can take 2 minutes to tell you the interesting properties of these. Okay, so there is a way of saying when these things have completion. I won't write it down. So let me just say completion tick. And this generalizes corner completion for cubes and also cone completion, and also things like gluing two cubes together along a face. That corresponds to completion of these prisms and tricube completion and all those things. But okay, so what's true? So these things, by abstract nonsense, instead of having two-fold homotopy groups, they have as many fold as you like homotopy groups. So these have iterated homotopy groups. So, pi a1, pi a2, up to pi ak of x. Please close the brackets in your own time. Moreover, if I take the pi1 of pi1 of pi 0 of x, again, just using this abstract nonsense definition that forces these groups to exist, this is actually precisely ak of x if, oh, I didn't write this down. If x is a cube space, I can sort of fill in all of these other sets in an obvious way, right? There's a way to extend a cube space to this more general object. And if I do that, then this iterated homotopy group is precisely the structure group. And I guess the final thing, well, I was going to tell you the idea behind this, but I definitely don't have time. So let me just finish by giving a conjecture. So one of my reasons for wanting to do this is because these sigma simplicial sets are sort of a generalization of both simplicial sets and of cube spaces. And I claim that you should be able to finally tie this over. So I claim there exists a functor from these sigma simplicial sets to normal simplicial sets. Such that now if I apply this functor to x and then take its honest simplicial homotopy groups, then this will also just be the normal structure groups of x. So in other words, I expect to be able to take a cube space, extend it in an obvious way to this more general object, the sigma simplicial set, and then map that into honest simplicial sets, and then just like apply all of the homotopy theory in the world to that. And it should correspond to things that we already do to cube spaces. Okay, I'm definitely beyond time, so I should stop there. Oh, so it's a little bit roundabout. The link with directional Gauss norms is that, so I think these correspond to certain non-symmetric cube spaces. So here I assume that the up edges and the across edges are the same. For directional Gauss norms, they might be different. And then there's sort of more going on. And I think you need to understand the homotopy theory of these bi-tri something simplicial sets that might not be symmetric. I don't know of any new norms you get off the top of your head. Yeah, this is short on applications at the moment, but I think it certainly should be possible to find sort of factors corresponding to these things. But yeah. Oh, So in the simplicial set world, you almost never have unique completion. So they don't really like that idea. Here, I didn't really, but yeah, I mean, in general, having unique completion will correspond to eventually all of these structure groups being 0. In the simplicial set world, so for them, everything's much less unique. Everything is always up to homotopy, right? So it's like, they don't like having a unique way to do things, just being sort of all the ways of doing it are the same. So for them, they would just say that all of the homotopy groups eventually vanish. That's an interesting kind of space, but it wouldn't correspond to unique Khan completion. I don't know if that answers your question or not, but right. So you can always take one of the quotients pi k of x where completion will be unique by definition. Yeah. And I think that side is basically staying the same.